Today we're going to be talking about the t-test. Now the t-test is very, very similar to the z-test. So we're going to begin with a little bit of review about how the z-test works. Because we're working in a Colab Jupyter notebook here, we're going to need some packages. We'll use the pandas package and we'll import that as PD. We'll use the stats package from the scientific Python package, and later we're going to use the square root function from the math package. So I'm importing those things here. Now let's talk about the z-test for a mean. Now, every z-test will have a hypothesis, an alternative hypothesis, and a null hypothesis. And the simplest form that these hypotheses could take is they could be stated in terms of the mean of some population is going to be greater than some fixed value. Now, there are alternatives here. We could state that the mean is less than some fixed value, or we could state a two-sided hypothesis saying that the mean is unequal to that value. We could even get more interesting still. We could talk about two different populations with two different population means. And the alternative hypothesis could state that they are unequal, or could state that one of them specifically is greater than the other one. In all of these cases, we have z-tests. And in all of these cases, we're going to have analogous t-tests that will be sort of similar but different. So how does the z-test work? Well, we identify some sort of alternative hypothesis and some sort of null hypothesis, and then we have the test mechanics. We begin, of course, with sampling because we have to measure something to evaluate the test. We identify the sample size, n. If there are multiple samples, we identify the sample size of each. We identify the sample mean, x bar. If there are multiple samples, we have to identify each. And we identify this sample standard deviation. And I'm just making up some numbers for all of these here. Then on the basis of all of this information, we calculate a standard error. Now the formula for the standard error of a mean is sigma over the square root of n. And then when we have our data here, we have to have something to plug in for sigma. Now, this is kind of a key step here. We don't know sigma exactly, but we do know s. And for the purpose of calculating the standard error, we plug in the value of s for sigma. S and sigma are probably close to one another, and so it's probably fairly safe to plug in S for sigma, but we'll come back to this problem soon. Then with the standard error in hand, we calculate the z-score. The z-score is always calculated as a measurement minus some expected value divided by the standard error. And then once we have the z-score, there are several different ways that we can calculate the p-value. We can use an online CDF calculator, such as this one, or we can use the function stats.norm.cdf and just plug in the z-score. Remember, stats.norm.cdf calculates a left tail, so if we want a right tail, which is typical, we have to subtract from 1. That's why I'm subtracting from 1 here. Or we can use a z-table to evaluate the strength of the hypothesis. Now, sometimes so all of this is how we calculate how we perform a z-test, and much of it is the same as the way we calculate a t-test. I want to remind you how this would look if we're testing two populations against each other. We might have an alternative hypothesis that says one mean is less than another mean, or if we wanted a two-sided version of the same thing, we would simply state inequality between these without stating specifically which direction it goes. And then, of course, we'll have a null hypothesis that states equality between two population means. We'd have to collect data about sample sizes for both populations, about means for both populations, about standard deviations for both populations, and about standard errors for both populations. We'd use this formula twice, sigma 1 over square root of n1 and sigma 2 over the square root of n2 to calculate both standard errors. And then we would synthesize these into one big standard error. This would be the standard error for the difference between the means. And then this is the standard error that we would use to calculate the z-score. The z-score in this case would be the measured value of the difference. This hypothesis would be phrased mu2 minus mu1 is greater than 0, mu2 minus mu1 is equal to 0. And then we would take the measured value of the difference, mu2 minus mu1, which would be x bar 2 minus x bar 1. Then the expected difference would typically be 0, and we divide by this standard error for the difference. This would calculate a z-score for the difference between two means, and then we would calculate the p-value using any of the same tricks. Now, let's talk about the problem with the z-test. There is a fundamental problem with the way we calculate a z-test, a fundamental inaccuracy in the way that this works, and it's here in bold. The fundamental inaccuracy of the z-test is that we have a formula for the standard error, sigma over the square root of n, and we plug in s for sigma. Now, S is not sigma. S is the sample standard deviation. Sigma is the population-wide standard deviation. We should plug in sigma for sigma. We should know the value of sigma and plug that in for sigma. In theory, we should, but it's impossible to do so because from a simple sample, without having a census of the entire population, you can't possibly know the true value of the population-wide standard deviation. So we can't possibly plug in the right value for sigma. S is the next best thing. But nevertheless, the substitution of S for sigma in this formula gives us a thematic underestimation. We underestimate the standard error and therefore tend to miscalculate the z-score. Now, is this effect very serious? No, it's actually not very serious in most cases. In fact, for almost any study with a large sample size, this effect is so minor that we can safely ignore it. But particularly for studies with small sample size, the difference between S and sigma can be pretty significant. And so the substitution of S for sigma can be a pretty bad mistake. And so that means that the z-test is kind of fundamentally flawed in a way that is serious for small sample sizes, but not very serious for large sample sizes. That means that if you're working on a study with a very large sample size, you can completely ignore all of these problems. You could ignore the inaccuracies of the z-test will work just fine. But if you're working on a study and you only have a sample size of 15 and you're still trying to conclude everything that you can, the responsible thing to do is not use the z-test at all, but use the t-test, which is built to compensate for this error. Now, with this description of the problem, if I start trying to sell you a solution to this problem, then you might think the solution is to do a better job calculating sigma, right? Use some sort of trick to do a better job calculating sigma instead of just substituting S. And that is what we would do if we knew how, but that's not something we know how to do because sigma requires the rest of the data from the rest of the population. We can't do that. So instead of correcting our estimation sigma for S, we continue to use S for the standard error, but we can correct the distribution to which we compare it. That is, instead of what we're going to do is we're going to sort of admit that we've got an inaccurate calculation of the t-score for this test statistic. And then we're going to say, well, if it's inaccurate, then that inaccuracy affects the distribution that that thing will have in the null hypothesis case. And that means that we shouldn't actually be comparing it to the z distribution at all. We should compare it to a slightly modified distribution. And that's the solution which the t-test offers. Basically, go ahead and calculate the z-score just the same way you did. We can call it a t-score or a t-statistic, but it's really exactly the same thing. The real insight here and the real modification is not to calculate the thing differently, but to compare it to a different distribution, which is built to compensate for the error between sigma and S. And so we have a t-distribution. Now the t-distribution looks like a bell curve. It looks almost exactly like the z-distribution. And let me show you how this thing looks. If I have some degrees of freedom here, we'll get to what that means in a second. This is a typical t-distribution, and it looks just about exactly like a bell curve. And in fact, if the degrees of freedom are rather high, this is almost exactly a bell curve. And so, so no worries. But it's a slightly modified version of the bell curve, and it's modified to correct for the error of replacing sigma with S in this calculation of the standard error. So the idea here is to introduce a new distribution. And then instead of comparing the z-score to the standard normal distribution, we're going to compare it to this t-distribution, which is a modified bell curve. Like the chi-squared distribution, the t-distribution depends on a degrees of freedom variable. But unlike the chi-squared distribution, it depends on the sample size alone. So the chi-squared distribution has a degrees of freedom, which depends on how many categories you're measuring. But the t-distribution depends on a degrees of freedom, which is equal to simply n-1, where n is the sample size itself. So if you have 1,000 data points, you have 999 degrees of freedom there. So let's talk about the steps for the t-test in theory, and then we'll do some worked examples. Basically, a t-test is exactly the same thing as a z-test from start to finish. Whether you have whether you have one sample and whether you have one sample like this and you're comparing the mean to a fixed value with a two-sided or a one-sided hypothesis, whether you have two samples and you're comparing two means to each other with a one-sided or a two-sided hypothesis, everything is exactly the same down to the calculation of the z-score. We call it the t-score or test statistic, but it's the same thing. It's the measured minus expected over the standard error. So everything for a t-test is exactly the same down to this stage. The only thing that's different is the distribution to which we compare that score. When we get our test statistic, we do not compare it to the normal distribution. So we don't use a z-table. We don't use this function. We don't use the normal CDF calculator. We use instead a t-test CDF calculator, or we use the t-distribution here, or we use not a z-table, but a t-table. These are the only differences. And so if you're familiar with the z-test and you really understand the ins and outs of the t-test, of the z-test rather, then performing a t-test is really only a little bit more information. It's only a little bit extra to do. Notice that this calculation, stats.norm.cdf, which calculates the p-value from the z-score, depends on only one input, which is the test statistic z. Notice that stats.t.cdf, the calculator of the p-value for the t distribution, depends on the test statistic, which is here called x, but also depends on the number of the degrees of freedom. And so we have two inputs to this function. But other than that, it's really simple. It's very much the same. If we don't want to go to all the trouble of calculating everything for ourselves, then just like the chi-squared distribution, there is a canned solution. We just call the right function and it will start to finish calculate the t-test result for us on the basis of raw data. So if you're doing, if you're a statistic, if you're really doing a lot of statistics and you need to make your life easy, then you just rely on the right formula here. So long as you know what it's doing, it'll work just fine. So what we're going to do next is we're going to do some worked examples where we walk through all of these calculations by hand. And I also illustrate how to use the computer to calculate these things directly from data. Now, in your homework problems, you might not always have the luxury of using these canned solutions precisely because you're not given raw data in the homework problems. You'll be given summary statistics about the data, and then you'll have to put them together using the process described. All right, so let's look at our first worked example. Our first worked example is a birth weight example. We're going to load this data set, NC, I forget what it stands for. This is data set about 1,000 newborns, and it comes from our textbook publishers. So we're going to load this data set, and then here is some of the descriptive information about that data set. So we have father's age, mother's age, weeks of the pregnancy, visits, weight gained, I believe, and then this is the weight. This is the birth weight in pounds of the newborn, and so that's the variable that we're going to focus on. Notice that the average birth weight is listed as 7.1. That's not 7 pounds 1 ounce. That's 7.1 pounds. So that's slightly heavier than 7 pounds. We're just going to use this data set and run a simple hypothesis test. Our hypothesis is going to be, is the average birth weight statistically significantly greater than 7? So we can see here clearly that the average birth weight within this sample is 7.1. But is there a statistically significant difference between this measurement and 7 itself? So that's the test that we're going to run. Now, in order to run the test, we're going to need the basic descriptive statistics about this, which would generally be given in a story problem about this data. But here we're going to have to compute them for ourselves from the data. So we're going to take, notice the data frame is called df here, not to be confused with degrees of freedom, right? This is df for data frame, not for degrees of freedom. So the data frame is called df, and we're going to take the weight series particularly, and then we're going to ask for its mean and its standard deviation and its count. And we're going to assign those to variable names x bar, s, and n, which are the calculations described up here. We need n, we need x bar, and we need s. So that's going to be the basic descriptive statistics that we need on our data set in order to get started. So those will calculate those things. Then we're going to need calculations of the standard error and the z. Now, again, notice I'm plugging in s where I should have a sigma for the standard error because I don't know sigma and s is the next best thing. So s over the square root of n is how I'm going to calculate the standard error. And then the z-score is the measured value minus the hypothesized or expected value divided by the standard error. So this is how we always calculate the z-score, measured minus expected divided by the standard error. This is also the t-score because we're doing a t-test now. But it's the same calculation, and nothing here is any different from what we would do for a z-test for this hypothesis. Then, so these lines are kind of fancy, but these are just printing out all the information we've got so far. X bar is 7.1 as we measured here. We've got S, we've got N, we've got a standard error, and we've got a z-score. And a z-score of 2.117 looks pretty good, right? A significant z-score is up in the range of 2 or higher. So this looks pretty good. It looks like we might have a statistically significant result. Now, this is where normally we would go to the bell curve and we would say, okay, how does this fit on the bell curve? And what's the tail weight on the bell curve? But now we want to do the t-test because we want to compensate for basically this error here of plugging in S for sigma. So we're going to do a t-test instead of a z-test. So how do we do that? Well, we have three options for resolving the test. The first is to simply use the function stats.t.cdf. So basically, from the stats package, look at the t distribution and look at its cumulative distribution function. Just like for the normal stats.norm.cdf, we have to subtract from 1 because this is going to give us a left tail. So the p-value is going to be 1 minus stats.t.cdf. And notice what I have to plug in here. I have to plug in the prior calculation of z, which is 2.117, and I have to plug in the degrees of freedom. And I could write just as well n minus 1 here, right? N is 1,000. So I'm plugging in n minus 1 for the degrees of freedom because n is 1,000. And when I calculate this, then I'll get this value for the p-value. Now that is wrong, and I think that doesn't look reasonable to me. So let's recalculate everything. I think I was using some bad data there. So we'll calculate this value for the p-value, and we'll get 0.017. Now, that will allow us to resolve the hypothesis test. So what do we do to resolve here? The p-value is 0.01. Assuming that the threshold of significance alpha is 0.05, then the p-value gets underneath alpha, so we reject the null hypothesis. In other words, we reject the hypothesis that the average weight is 7 pounds, and we favor the alternative hypothesis that it is significantly greater than 7. This is maybe a bit of a surprise here, because the weight was so close to 7, you might have expected that there is no significant difference from 7. But here we are seeing that we do get a statistically significant difference from 7. And really the reason for this is because we had a very large sample size and a very small standard deviation. And so we were actually able to measure quite accurately, and that's why we have a statistically significant result, even though the difference is small. This is a good time to remind you that statistically significant is not the same thing as important. What we have here is statistical evidence that there really is a difference between the average weight and 7 pounds. Now, whether this extra 0.1 pound actually matters in the world, I don't know. What we have here is a measurement that the effect is real, not necessarily a measurement that that 0.1 pound is significant in the sense that it's important to the health of the newborn. Although it certainly could be, right? I'm not saying it's unimportant. I'm just saying that we can say that it is statistically significant, this effect. That basically means the effect is real. That's not the same as describing whether the effect is really very important. Okay, so that's one way we could resolve it using stats.t.cdf. What's another way? We could use a t distribution calculator. So let's do that. The calculator is going to need the degrees of freedom, which is 999, and it's going to need the test statistic. And so we plug those in and we get 0.017. which is just the same as the result we got before. Notice this calculates the right tail. If we wanted a left tail for some reason, we could get it this way. If we wanted a two-tailed test, perhaps because we wanted to do a two-sided hypothesis instead of a one-sided hypothesis, then we could get it this way. But honestly, you wouldn't really need to do that, because if you have the p-value for the right tail, then you can just double it to get the p-value for the left tail, because the t-distribution, like the normal distribution, is left-right symmetrical. So the left tail and the right tail would be the same size. So this is another way to get the p-value, p-value 0.017. That tells us that we are significant, and so we have a real effect. And the third way to get the test resolved is to have a t-table. Now, this is here, what I'm doing is kind of weird. I would never really do this in a Jupyter notebook, but I'm specifically building a t-table in the Jupyter notebook, which is kind of an odd thing to do. If you're working in a Jupyter notebook, you probably don't need a t-table in the first place. You should use these other functionalities. But sometimes you're not working in a Jupyter notebook. Sometimes you're working in just pencil and paper and maybe a basic calculator. And so you need to use some lookup table in order to resolve the test. This is called a t-table, and like a chi-squared table, you have to know what to look up in order to get the test resolved. You need to look up just like the chi-squared table, you look up the threshold of significance across the top here, and you look up the degrees of freedom across the side. And that doesn't tell you the p-value. That will tell you the critical value, which is another way of saying it's the value to beat in order to get significance. So here, I'm going to look up 0.05, this column here, because that's their standard value of the threshold of significance, 0.05. And which row am I going to use? I'm going to use row 999. So I'm going to scroll down here. These rows will come faster and faster. And typically with a t-table, you don't get like every row because that would take forever, but you get to look up the closest. So the closest row that we have to 999 is 1000. And we look up this value because it's in the column corresponding to alpha equals 0.05, and I get 1.65. That's not a p-value. Obviously, it can't be a p-value because it's greater than 1. What that is that's a critical value. That's the value that the test statistic must beat in order to have a statistically significant result. Now, what was our test statistic again? Oh, yeah, it was well, it's not there anymore. It was 2.117, right? Where was it? It's here. 2.117 was our test statistic. So we're comparing it to this value, 1.65, and it does beat that value. And that means we have a statistically significant result in this case. So that's how we would use the t-table to resolve this test. Look up this alpha, look up the degrees of freedom, find the critical value, and then ask, did we beat that critical value with our test statistic? And indeed, we did. So again, we would conclude, hey, that is a statistically significant result. The birth weight is in a statistically significant way greater than 7 pounds. Now, those are 3 ways to resolve the test using the t-distribution if we have performed the test by hand. And notice that performing the test by hand is basically just a z-test. The only real difference here is how we resolve it using the t-distribution. Now, I want to show you one more strategy here, which is to perform the test entirely from the data using this canned function t-test one sample. So this is not an L here. This may be a little hard to read. This is t-test underscore numeral 1 samp, because this is a one sample t-test. It's one sample because we have only one data series that we're actually analyzing here. So the inputs to this test are the data itself. This is the entire data series of weights itself, not some statistic calculated from it, but the data series itself, and the comparison value that we want to compare it against. And notice something that's missing from this command. What's missing is the directionality of our one-sided alternative hypothesis. Remember, our alternative hypothesis in this problem states that the weights on average are greater, specifically greater than 7 on average. And nowhere in this am I saying, I want you to test that it's greater than 7. I'm just saying, I want you to test it against 7. Okay, so that's a little suspicious. What happens when we run this command? We run this, it plugs in, It didn't work. I don't know why. That's kind of fun. I think it's probably because this didn't get evaluated. So let's try this again. There we are. Okay, it worked. I don't know quite what happened. So I plugged in these weights, and notice the test statistic comes out again 2.117, just as we expected. But hey, wait a minute. The p-value is 0.034. What happened here? What was the p-value that we calculated by hand? It was about 0.017. It wasn't about 0.034. What gives? What's up with the p-value? This p-value is about double the p-value that we calculated by hand, right? 34 out of 1,000 compared to 17 out of 1,000. So this is about double what we calculated by hand. Did this mess up? No. This performs by default a two-sided hypothesis test. This did not test the hypothesis that the weight is greater than 7. This tested the two-sided hypothesis that the weight is different from 7. And so this had a side effect of doubling our p-value because it effectively automatically calculated a two-sided hypothesis like that. And that's why we got 0.034. Well, if this is how we want to work our tests, then we have to be aware of this, right? What if I wanted a one-sided hypothesis? Well, no matter, you just grab this p-value and divide it by 2, right? Because you know that the relationship between a one-sided hypothesis and a two-sided hypothesis is whether or not that p-value is supposed to get doubled. So if this is by default just giving you a two-sided hypothesis test, and what you really wanted was a one-sided, well, just take the p-value and divide it by 2, so no worries. So that's why the p-value is different, and that's what to do about it if you're annoyed that the p-value is different because you wanted a one-sided hypothesis. This is not because we had a one sample, right? Notice that the one sample question is about what is the structure of your data. The two-sided, one-sided question is about whether your hypothesis is going to state a difference with directionality or simply a difference. Now, let's look at our next example. In our next example, we're going to be studying this blood transfusions example. This is a better candidate for the t-test because we have a very small sample. I want to point out here that so in the previous example where we had these birth weights, we actually had 1,000 birth weights in this data set. And so, as I said earlier, the t-test is an important correction, especially when the sample size was small. Well, if in the birth weights example, the sample size was big, we didn't really need the t-test. But in this mouse example, the sample size is going to be rather small. And so it's more important for us to do a t-test. So that's the first change. But the more important change is this is going to be a two-sample test. In other words, this is going to compare one sample to another sample, and it's going to compare the means between one group and another group instead of comparing the mean in a single sample against a fixed value. So we don't really care about what the data are in reference to any single fixed value. What we really care about is whether one group has larger values than the other group. So let me explain this experiment a little bit. We have 30 mice, they receive blood transfusions. Their energy level is monitored later with an exercise wheel. But some of the mice receive blood transfusions from other mice who are young. And some of the mice receive blood transfusions from other mice who are old. The mice receiving the transfusions are older mice. So the idea here is, can the transfusion from the blood of the younger mouse actually increase the energy level or health of these older mice? So there is a little bit of data management to do first. We have to load the data, and then we have to split the data into the data series that is just those receiving the old blood and just those receiving the young blood. So we have two different data sets here, the old and the young, and we have to do separate computations for all of them. We'll say X bar 1 and S1 and N1 are the relevant descriptive statistics for the old sample, old.mean, old.standard deviation, old.count, right? So whatever we get for these will be describing the mice that receive the older blood. Then we've got the same thing going on for the younger blood. And then, because we're comparing one sample to another sample, we have multiple standard errors to reason about. we have the standard error for the old group, then we have the standard error for the young group, and then finally, we need to combine the standard errors to get the standard error for the difference, which is this Pythagorean combination, SE1 squared plus SE2 squared square root. So that's like the Pythagorean theorem. This is the standard error for the difference between the averages of the two groups. And then finally, we need to calculate the z-score. Now, we need to be careful here. The z-score is always the measured minus the expected divided by the standard error. But what are we measuring and what are we expecting? If the form of the hypothesis is that the mean for the young mice is going to be greater than the mean for the old mice, then what we're measuring is not one mean or the other, but the difference between them. And so this is the measured value for the difference between the means. This is the expected value for the difference between the means if the null hypothesis is true. So if the null hypothesis is true, there should be no difference at all. So this is you want to think of this as the measured difference, and then you want to think of this as the expected difference, and then we divide by the standard error, but it's specifically the standard error for the difference that we're dividing by, and that will give us a z-score. So we do all of these computations, and we get a z-score of about 3.2, which is pretty good. That's a pretty high z-score, and that reflects that we probably have statistical significance. So how do we resolve? So I want to remind you here, everything I just did here was typical for any z-test, right? If I ask you to do a z-test to test one sample against the other, except for this little trick to divide the samples against each other, everything we did here is exactly what we do for any ordinary z-test. So what we would do next if we were doing a z-test is we would compare this to a standard normal distribution. But we're not doing a z-test here. We're learning how to do a t-test. And so we're going to compare this to a t-distribution instead. So option 1, we just use stats.t.cdf. And notice here that I need to plug in not only the measured test statistic, which is the z-score or t-score, but I also need to plug in the number of degrees of freedom. And this is actually now a hard question. How many degrees of freedom are there? So if you remember here, when I discussed the t-test solution specifically, I said, well, we have a degrees of freedom, and the degrees of freedom is going to be n-1 for a one sample test. So that's why we had 999 in the previous example. But here, we don't just have n-1, right? We have n1 and we have n2, and I didn't print their values, but they turn out to be 13 and 17. So if we have a look at n1 and n2, n1 is 13. There are 13 mice that are getting the old blood, and n2 is 17. There are 17 mice that are getting the younger blood. And so should we use 12 or 16 or some combination of those numbers? That's not at all clear. And actually, it's a bit complicated underneath the hood. So there are two ways to go about this. The first way is to pull out some ridiculously complicated formula for synthesizing the two degrees of freedom to make one master degree of freedom, much like we did here. That's possible, and long term, if you're working in this industry, that's the right thing to do. But honestly, it's just too darn complicated for our purposes, and I want to give you some guidance to do something that's simple and accessible and won't drive you crazy. And so there's a sort of a conservative approach here, which is close to being correct and is reasonable. And so that approach is to take the smaller of these sample sizes and subtract 1 from it. So we're going to take n1 and we're going to just subtract 1, and that's going to give us 12. Is this the right degrees of freedom? Well, it's a good way of estimating the true degrees of freedom. It's not the exactly perfect formula for the degrees of freedom, but it's close enough for a 100 level class, and that's what we're going to do. So we're going to plug in 12 here. 12 because it's 1 less than 13, and 13 is the lesser of these sample sizes. So that's why I'm choosing 12. Now I'm plugging in the test statistic from above. which is 3.2. And I'm subtracting from 1 because I want the right tail, not the left tail. And we get a p-value 0.0038, which is great, right? And we know what to do with a p-value that small. We reject the null hypothesis because it's less than alpha. And what does that mean? That means, well, the null hypothesis was that these two groups were going to have equal exercise measures. And this means that the mice receiving the young blood are exercising more. What does it mean? I mean, it would be tempting to interpret this to mean that like receiving the plasma of young mice makes the mice healthier or hardier or stronger. I mean, it would be tempting to interpret like that. That may be true, but we should always interpret scientific results cautiously. It makes them exercise more. It might not actually make them healthier. See, it's not the same thing. Okay. Our second alternative for calculating the p-value would be to use our z-score of 3.2 and our degrees of freedom of 12 and plug it into this t-score calculator, and we'll get 0.0038 again. And it's just this tiny, tiny sliver here of this graph being displayed there that represents the right tail that we need. So again, we get the p-value. And the other way we could get the p-value, well, the other way we could resolve the test is we could use the t-table. So let me illustrate how we would do that. With 12 degrees of freedom, we would look up 12 on the left-hand side of this table. With an alpha of 0.05, then we would use this column. So we would look up until we got here 1.78. That would be the critical value. So what does that mean? That's not the p-value. That's the critical value. The test statistic must beat that value in order for us to get statistical significance. And it does, and then some, right? The test statistic is 3.2, so it beats this value quite soundly, and that means that we reject the null hypothesis and that the blood really did have a real effect. So whichever of these processes we carry out, we detect that we do have a statistically significant result. So the blood transfusion has a real effect. So again, I want to illustrate how we would do this as a fully automated test after splitting the data frame into young and old. So remember, I split it into old and young up here. Then I would just take those particular data series and I would perform what we call a t-test for independent samples. So this is not the same t-test. This is now a two-sample t-test from, so we did one sample before. This is a t-test for a two-sample situation, comparing the young sample to the old. And I'm gonna throw in this little option here, equal variance false. Basically what I'm saying here is I don't want the computer to assume that the standard deviation among the old mice and the standard deviation among the young mice would necessarily be the same in the null hypothesis. So so here we go. We're going to run this thing, and then we run it, and we get a result. And notice that the test statistic is about 3.2 as before. But notice that the p-value is not the same as the p-value that we got here, 0.00382. It's just a little bit different. And there are actually two reasons why the p-value will be slightly different. And I want you to understand. First of all, like before, this is actually by default calculating a two-sided hypothesis. And so this is a p-value for the two-sided hypothesis. We should cut this p-value in half in order to get the real p-value for a one-sided hypothesis. But that makes it even farther from our real value. The other reason this p-value is going to be different from what we calculate by hand is because this test uses a much more sophisticated calculation of the true degrees of freedom for a for the two-sample t-test that depends on effectively it depends on both of these standard errors and both of these n values, and calculates the degrees of freedom in a different way, and it has more. It identifies more degrees of freedom in this result, and therefore that changes the p-value. So we're going to get a slightly different p-value, but it's going to be sort of in the same ballpark as the p-value that we calculated by hand. So it uses a sophisticated formula for the degrees of freedom, which you can use too. If you want to look it up, then you can use that formula. It's not it's not super hard, but it's just a bit much for us. So I'm trying not to go overboard. All right, so that's the fully automated test for the blood transfusions, which is a 2-sample test. Now, okay, so what's the basic structure here? The birth weight question is a 1-sample test. The blood transfusion question is a 2-sample test. Here we compare a mean against a fixed value. Here we compare two means against one another. The final example is a marriage example. It's about the studying the question, are husbands older than their wives? And it's not clear in this example whether we should be doing a two-sided or a 2-sample or a 1-sample test. And so let's look at some data and examine this question. So here's what our data set looks like. It's just a whole bunch of heterosexual married couples with a husband and a wife identified, and their ages are given. All right, so that's simple enough and innocent enough. Now, we clearly have 2 samples. We have a sample of husbands and we have a sample of wives. We could calculate the average husband's age and the average wife's age and the standard deviations of each and the n value for each, which is actually 105, not 104, because it starts numbering at 0. So we could do all of that, and we could mimic exactly what we did here for the blood transfusions. That would be fine. Or we could automate the thing, and we could just calculate it directly using a t-test for independent samples. And that's what I did here. So this is the quick and easy and wrong way to address this hypothesis. Again, let me remind you, the hypothesis is husbands are older than their wives. And the null hypothesis would be that the average age of the husbands and the average age of the wives will be equal. So this is a quick and easy and wrong way to solve this problem. We're going to use the same thing that we did for the blood transfusions, the t-test independent. And so here I'm just going to plug in the ages of the husbands as a data series and the ages of the wives as a data series, and then I'm going to get a result. And notice the p-value is 0.07. So this says we do not have a statistically significant result because 0.07 is greater than 0.05. However, this is the wrong way to do this test. Effectively, what we're doing here is we're comparing the husbands as a collective, as if they were all just bunched together, and then the wives as a completely separate collective. So basically, take all the husbands and put them in one big room. Take all the wives and put them in one big room, and then treat the husbands as a data set independent from the wives. So the problem with this treatment is the husbands are married to the wives and the wives are married to the husbands. They are naturally paired off, and we have ignored this pairing. So there may not be significant differences between the entire collection of husbands compared to the entire collection of wives if we ignore the way that they're paired off. But they are paired off. And if we look at the individual marriages as pairs, we might be able to identify a statistically significant trend on the level of from one marriage to the other. So this data, this type of data, where we have numbers here to be compared with numbers here, but they naturally pair up. We might have similar data like before and after data, before and after some drug treatment, or before and after some educational thing, then you would measure some pre-test, post-test thing. Data like this where each case is basically representing one thing, in this case a marriage, and different facets of that thing is called paired data. And when we have paired data, it's usually a pretty bad idea to completely unpair it and consider one whole data series as a completely separate thing from the other data series. So we would probably get a stronger result if we remembered that these were paired. Now, how can we do that? Well, it's so that's a summary. So I've identified the flaw, and the fix is to regard them as paired. How do we actually do it? Well, it's pretty simple. We take our data frame and we introduce a calculation of the difference in the ages. So I'd like to show you, before we do this, what the data frame looks like after we do this. But I need to get that loaded again because I didn't re-execute this loading command. So let's get that loaded again. And then this will be this flawed approach. And then here we calculate the difference. So by saying data frame difference column is equal to data frame husband column minus data frame wife column, then we get these differences. And notice that the differences are husband's age minus wife's age, which is typically positive here, but sometimes negative. If the wife is older, this will be negative. If the husband is older, this will be positive. And if they have the same reported age, then this will be 0. So this is the difference column. And now basically what we can do is we can say, let's compare the differences themselves to 0. Are they on average greater than 0? By only reasoning about the standard deviation of the differences, then we're only kind of reasoning about the level of variations here. Notice that this difference column has much less variability than the husband column, and it has much less variability than the wife column, because these are husband and wife pairs of all kinds of different ages, right? These are in their 60s and these are 20s and 30s. So these are all different ages. There's huge variability among the husbands. There's huge variability among the wives. There's little variability among this differences columns. And this is really where the reason why we get better results by considering the data as paired. So if we calculate this difference column, then we can perform a one sample t-test for the difference column by comparing it to 0. And what will we get? We'll get a p-value of 7. Wait a minute, 7? How can 7 be a p-value? Oh, wait, it's not 7. It's 7.12 times 10 to the minus 8th power. This is a tiny, tiny number. It's 0.0000, lots of zeros, and then 712. So this is a very, very tiny p-value, and this tells us that we get a very strong, statistically significant result. And we can conclude that husbands are older than their wives to a statistically significant degree. And so we see here, we had a very weak result by considering these as independent and forgetting that they were paired. But when we treat them as paired and calculate the one sample t-test for the differences, then we can see we get a very strong result, and we conclude that the husbands are indeed older than their wives in a statistically significant way. Whether that's socially important, I don't know. That's not the same as statistically significant, but we do get a statistically significant result here. Now, I wanted to illustrate the same thing by hand. So we need to calculate the x bar and the s and the n, and we don't have number 1 and number 2 here because this is all one sample now. We're only reasoning about the differences. So x bar is the mean difference. This is the standard deviation of the differences, which is rather small. This is the count on the differences, which should be 105. And then we get a standard deviation for the differences, just treating it. It's not the standard deviation for the difference between two means. It's the standard deviation for one data series, namely the difference data series. And that's why we just use the simple formula. And then the z-score is the measured value minus the expected value. Why is the expected value 0? Because the null hypothesis says there should be no average difference between the ages of the husband and the ages of their wives. So that's why we compare to 0 here, x bar minus 0, and then we divide by the standard error. We get the report there, and notice the z-score is 5.8, which is an enormous z-score, and that's a very strong result. Resolving the test by the t-test means we have to plug in the right number of degrees of freedom. So we use stats.t.cdf. We plug in the z-score 5.8 from above, and we plug in 104 because n was 105. And then we get this value here. Now, this value might look different from the value that we got before. It is different. It's half the value because this is a one-sided hypothesis. And remember, as we talked, this by default calculates a two-sided hypothesis. If you divide this number by 2 in order to get the one-sided p-value, then you'll get this number here. We can also use the online CDF calculator. It doesn't work so well in this case because the z-score is, well, the t-score is so very large. I think it was 5.8. Yeah, 5.8. And this thing will just measure 0, which basically means the p-value is so small that this calculator can't measure it. And that's a typical result from a simple applet if you get a very small p-value. And then we can do this from a z-table. The result is so strong that we hardly need to, but let's do this from a z-table as well. If the threshold of significance is 0.05, then we need to look up next on this column, we need to look up the number of degrees of freedom, which is 104. So we're going to read in the second column, and we're going to look up 104. Now, these numbers only go by fives, and then they skip and go by hundreds. So you can tell it doesn't make much difference here, right? 1.66, 1.66, 1.65. 100, the closest we have to 104 is 100, and so we get 1.66. This value is called the critical value. It is the value which the test statistic must beat in order for us to have a statistically significant result. Now, our test statistic is 5.8, which blows this out of the water and means that our result is strongly significant. So that's how we would resolve this by hand. So 3 types of t-tests: a one-sample t-test for simple data compared against a fixed value, a 2-sample t-test for comparing 2 populations, and a paired t-test for comparing some values against other values in paired data. Which one is appropriate will, of course, depend upon your data. The nice thing about a t-test is that 90% of the t-test is the same as the z-test. The only thing that's different is the use of the distribution of the t-distribution instead of the normal distribution to resolve the test and get the p-value.